Today we'll discuss the various fasteners that are shown throughout our catalog. We'll start with a brief company overview and a discussion of the PEM Edge services that are available to you in your design efforts. We'll mention what self-clinching fasteners are and how they work. And then through each bulletin, we'll go through and review the fasteners within those bulletins. PennEngineering is over 80 years old, and we are strategically located around the world to support our customers. So you can be confident we can work with you from the beginning of a design idea straight through production anywhere in the world. Look for our various trademarks to ensure that you're getting genuine PEM fasteners. PEM Edge is a suite of free services to help you get the information you need to make an informed decision. You can think of our application engineers as an extension of your engineering department. Can't find a part in a catalog? We quote over 250 customer-specific quotes every month, and we'd be happy to do that for you. Curious what would happen if you change materials, material thicknesses, things like that? Ask us those what-if questions. Our testing service labs are available to help you validate your design at no cost to you, and they are located in multiple places around the world so that we can work with you in the beginning of the design, but we can also help ensure that the original design intent actually occurs at the production site too. You can use our teardown service to help review your current and future designs. You'll learn of alternative fastening methods. We're not going to tell you what to do, but we'll show you what you can do. With PennEngineering, you have the opportunity to work directly with our applications engineers at your convenience. You may choose this via either the online chat, or you could schedule a virtual consultation with them. There are several reasons why customers choose self-clinching fasteners. One is certainly the strength of the threaded joint. These are stronger threads than you get had you tap the panel. It's faster operation. This leads to cost reduction, especially if you have high volume applications. If your product is formed in a stamping press, we can work with you to install these fasteners at very high speeds right within the die. These are in-die capable fasteners. Also, versus welding, there's great design flexibility. Our fasteners, clinching fasteners, can be installed into dissimilar metals, whereas with welding, it's best if the materials are the same. Here, you can install stainless into aluminum. Dissimilar metals are not a problem for self-clinching. It's a very clean process as well. It's very environmentally friendly. A lot less energy is required to run a press than it is to weld something in, and there's no secondary action that's needed, like to clean a weld spatter that's going to be necessary with welding. So there's been many reasons that customers over the years have gravitated towards clinching and away from welding. Here's an image of the most popular fasteners installation, the self-clinching nut. The logic I'll mention here is appropriate as well to self-clinching studs, standoffs, and other parts. Basically what we've established that the fastener must be harder than the panel. So as long as the panel is softer than the nut, we will have a feature called a displacer that takes up a certain volume of material, and as it's pressed in, that material is driven up into the undercut. When it's in this undercut, that gives us the push-out resistance. When it's in between the teeth of the knurl, that's what gives us the torque-out resistance. So again, as long as we know what the panel hardness is, we'll be able to choose the proper fastener that will be hard enough that when we drive it in, the fastener completely deforms the panel, and there's no deformation whatsoever of our fastener. Seen here are the three most common self-clinching fasteners: the nut, stud, and standoff. They all have their own unique shape, but they are all governed by a displacer, which will move material into an undercut and interact with a torque-resistant feature. There are obvious mechanical advantages of choosing self-clinching fasteners for design, and many of those are shown in the column on the left. But what's often overlooked is the fact that there's DFMA benefits of self-clinching fasteners. This is designed for manufacturing and assembly. This is the actual process of utilizing a part and getting it into the product. There's fewer parts to handle, there's going to be fewer assembly steps, there's less total assembly time, and this leads to what we call total installed cost. It is not the cost of a bag of 1,000 fasteners, as well as the actual cost to put those fasteners into the product, trust that they're going to work well, and have confidence that the end user, the ultimate customer, is pleased with the result. And so this total installed cost is a huge benefit as well by choosing self-clinching fasteners. Floating fasteners come in two versions, either a non-locking or a self-locking version. The purpose of these fasteners is the fact that the assembly allows that internal nut to move side to side. There's a radial float available. This is greatly helpful when there is mating hole misalignment. This could come from a design where there's a series of holes that must be perfectly aligned, and that can be difficult to do, especially when there's many involved. So by designing in some floating fasteners, you can take up some of that tolerance concerns you have and therefore greatly speed up your assembly. This fastener was chosen for two main reasons. The first is the fact that the fan that's used to cool the light in this projector, that's going to create the opportunity for vibrational loosening. So the LAC version of the floating nut was chosen to have that deformed thread and will prevent the screw from backing out from the nut. The second is the fact that this is a rather large unit. So the floater was chosen so that you can have misalignment accommodation during the assembly. So this enables a much faster assembly process, and therefore a little bit more expensive fastener can actually save money in the long run by speeding up the actual assembly time. There are two main reasons why blind nuts would be chosen. One is to protect against foreign matter from going from one side of an assembly to the other. Now this would be like dust and dirt. We do not claim that these would be watertight or gas tight. Our concealed head style of fasteners, which we'll discuss shortly, those would be. But for dust and dirt, that's one way to keep anything from this side of the assembly away from this side of the assembly. Another is to prevent potential damage when too long of a screw is chosen. Had this been a type of standoff where they'll be open at the end, if you chose too long of a screw, it could extend through the product and perhaps make contact with perhaps something electrical within the project. So you don't want that. So by choosing this closed end fastener, you prevent that possibility from occurring. This example here shows that concern where too long of a screw was previously used in a standoff, and when the screw extended through, the problem here is that it damaged sensitive electronic equipment. So by switching to the blind nut, had the wrong screw length been chosen, they simply would not have been able to create the full assembly because the screw head would be sitting further away from the panel. They know that they chose the wrong screw and have the opportunity to fix it. But with this scenario here, if you choose too long of a screw, you don't have the chance to fix it because you've already then damaged that electronics. So the B-nut can prevent that from happening. There are two main reasons why the concealed heads would be chosen. The first is typically cosmetics. You can see here, you do not see the head of any fastener, stud, or standoff. There is nothing showing here. That's because we've milled out a pocket and installed the fastener from the top side and clinched in, but it's into a milled hole as opposed to a punched or drilled hole. So therefore you do not see anything on the backside. That's typically the reason why these are chosen. But as I mentioned earlier, because of the fact that we have a milled hole and not a through hole, we do have the prevention of any dust, dirt, or liquid or gas going from one side of the assembly to the other side. So that is another reason why customers would choose this. The concealed head does prevent anything from going through the panel because it never was a hole through the panel in the first place. Cosmetics were the reasons the concealed head studs were chosen for this application. Here you see about 10 concealed head studs that are on the inside face of this black panel. They're facing into the center here and are assembled that way, but you don't see anything on the back side of this panel. It's a completely clean surface, and that was achieved by choosing these concealed heads and putting them into a milled pocket. The cassette is a new and improved solution to an age-old problem: how to get strong threads in a casting. If you try to tap that casting, it's soft, brittle material. You are not going to get good threads. So what people have done for a long time is use what is known as a wire or helical insert. But it takes a lot of effort to place it in there, and they've reluctantly been doing that, and they've been looking for an alternative, and that's exactly what the CastCert offers. There are more manual steps required to install a helical insert than there is for a CastCert. Casting creation is the same, but then for a helical insert to properly install, you've got to drill out that cast hole, whereas for a CastCert, you could use the as cast hole, whether it has a taper or not, no problem. And with the casting, after you've drilled it out for a helical insert, then you have to have a specialized tool, and there's a different tool for every thread size. So you have to have a bunch of tools if you're installing a range of these inserts. Then you have to manually turn in the insert. You'll see that on the next slide. And then ultimately you have to, most likely this is one of those inserts, helical insert with a tang, and then you have to break that off too. And then you also have to be concerned about finding that broken off tang so it's not a piece of metal that's rattling around within your product. It's a lot more manual effort to install a helical insert than there is with CastCert. This image here from McMaster Carr shows the several steps that are required, several manual steps that are required to properly install a helical insert. Again, this adds a lot of labor time and therefore cost to the install. So total installed cost, that is absolutely the way to think of the CastCert. The fastener itself in the smaller sizes will be less than a helical insert, but for all sizes, the installation absolutely is less than what it will take for a helical insert, and that's because of the great reduction in manual labor costs. Self-clinching nuts are the oldest of the PEM self-clinching fasteners and the most popular. They come in many different materials. This enables assembling to different panel materials. Some parts are designed for very hard panels. There's different styles of locking features available as well. This customer chose to replace 5 weld nuts with 5 self-clinching nuts instead. They were having issues with the positional tolerancing of the thread, and that was eliminated by the truer position available to them with self-clinching hardware. The ability to efficiently move large amounts of power through a system is something that we know is going to be growing for years to come. The electrification we see in automobiles and other markets requires this. So we are proud to offer the eConnect pin, which is offering our customers an alternative to the current methods for which they try to move this power. The actual usage of the eConnect pin will be recognizable to our customers. All we are doing is offering them an alternative method to either clinch it into their bus bar or adhere it to their PC board. The use of the mating sockets will be identical. The only real change will be the reduction in their total installed cost. The next in the growing line of eConnect fasteners is the contact bushing. This part is designed to provide very strong mechanical and electrical connections in both aluminum and copper bus bars. The PEM eConnect system will greatly improve and streamline your bus bar assemblies. It will reduce cost. No longer will you need to send the bus bars out to a third party for tin or more expensive silver plating. You'll no longer need to clean the bus bars in order to remove oxidation. Oxidation is a big concern because that can increase the electrical resistance. By choosing the PEM eConnect system, you're going to reduce the electrical resistance in your bus bar assembly. Next to discuss are flush nuts. These are basically just very short standoffs. They're flush at the top of the panel, and because they're so short, depending upon the thickness of the top panel, you'd select the flush nut that's appropriate. That'll be equal to or less than its length, and therefore you have the thread completely within the top panel, and you're able to put the second panel up flush against it. We have versions that go as well into stainless materials. That happens to be the F4. So again, solutions, essentially it's just a very, very short standoff. In this application, we show one of the big benefits of self-clinching is the fact that you get stronger threads than you would have had you tapped the hole. If this was tapped instead, you're only going to have the strength of an aluminum short thread. Now, with a clinched in flush nut, you've got a much stronger 300 series stainless thread in this design. And also with the being a flush nut, it's all in the same plane here. So what that enables is that this wheel assembly can be as thin as possible because it'll run in the track and we don't need to leave space for a nut or a screw head to be shown here. It's not necessary. It's all flush and in the same plane. The FE line of miniature fasteners, with their small footprint, are designed for space-constrained applications. They're available in both locking and non-locking versions. This miniature lock nut was chosen for this application because there is the concern that we're actually very close to the edge on three sides. So center line to edge distance is something that we note in the catalog. Typically it's just a one free edge. In this case, there's actually three free edges here. So they chose the smallest lock nut that we provide. The small footprint enables it to get into such a small space, but yet still provide the locking feature they need. Externally threaded self-clinching fasteners are available in multiple materials and head configurations, each appropriate for different applications. Flush head versions are often chosen for cosmetic reasons. In this application, there's self-clinching studs as well as self-clinching flush head standoffs that are installed into this metal panel. But then on the front side, this label can be applied over the top of it and you see no fasteners whatsoever. So again, these are chosen for cosmetic reasons. In this application, the customer had previously used 8 weld studs and 8 loose nuts. They were able to switch to only 4 clinch studs and therefore only 4 loose nuts. You can see here where previously the other 4 weld studs had been assembled. The problem here was the positioning of the fastener. The weld fastener didn't quite line up perfectly, and so with 8 of them, the variation between their fixed position was enough that when during the severe engine cycling tests they would put this through, they were having failures. But by switching to clinch, much truer position, they realized they could greatly reduce the number of pieces from 8 weld studs and 8 loose nuts down to 4 clinch studs and only 4 loose nuts. In this application, the customer required the strength of an M5 thread. They weren't able to drop down in size to an M4, but they were still in a space-constrained design. So they chose the FHL style, L for low displacement, and so less material is deformed. It's a smaller clinch profile, and therefore it's able to fit in closer to the edges, one a bend and one a free edge, as seen in this application. The IFH stud is a version of our flush head studs, which will enable you to achieve IPX7 and IPX9K ratings without the need for any rubber gaskets or sealants. When choosing a fastener for PC board applications, the RealFast surface mount line is the preferred choice now because of the elimination of any risk of board damage by trying to broach in a fastener. So the broaching style fasteners, they're still available for PC board applications, but for the most part they're more appropriate for brittle materials like cast magnesiums or cast aluminums. And when working with PC boards, the much more popular solution now is to choose the RealFast line. I start with this first application because it's a very good summary of what we call total installed cost. And that's not the cost of the fastener, but what it is the cost to get that fastener onto the board and then trust it. So the OEM had chosen a broaching fastener from a competitor, and they're fine with that. They didn't really know that there were other options. But the fabricator that they chose did know that PennEngineering supplied surface mount versions of those parts. So the fabricator went back to their customer, the OEM, and said, look, if you allow us to switch from broaching, which is fraught with risk, if you allow us to switch from broaching to PEM surface mount products, I could be more efficient, and then I can save money, and I can share some of that with you. So that's exactly what occurred, and that's what we talk about total installed cost. The PennEngineering RealFast part sitting in a tape and rip package, as an individual part, it's more expensive, but that's not the way anyone should look at it. They need to look at it, what does it take to get that part onto the board, trust that it's not going to damage the board and cause scrap, trust that it's going to stay adhered to the board and do the job it's supposed to do. And so the fabricator knew that what would happen. They went back, petitioned the OEM, and the OEM agreed, and then they happily switched from broaching to the PEM real fast. One of the main benefits of surface mount products is the fact that they do not apply any force to the board. They are not broaching, so we don't have to worry about how close we get to an edge, and that's really exemplified in this example here. There's a couple of the standoffs shown here. So in this close-up, you can see that actually standoff is hanging off the edge. The solder fillet is really only forming around 3/4 of the perimeter of the part. But that's okay. That's okay for the customer. They don't care if it's hanging over the edge. So in this application, it works fine for them. Had this been a broaching fastener, that absolutely would have cracked this edge. It would not have been possible. But the fact that it's surface mounted, there's no pressure at all applied to the board, and the solder fillet that doesn't completely go around the part still provided more performance than what they needed. A similar situation here. Again, this identifies what we call total installed cost. The customer had been using loose hardware. Loose hardware can be very cheap as simply a piece of metal, but it is the cost to get that onto the board and into the proper position and trust that it stays there. As you can see here, they noted that they had a lot of handling issues. Well, they don't have the handling issues any longer when they quickly pick the part out of the tape and reel, place it onto the board, it's reflowed, and then it's done. So again, total installed cost, we'll say that a lot, but this is another example of it where what had deemed to be a less expensive solution actually ends up costing more, and switching to the more expensive fastener ultimately saves them money. In this application, this customer was already using SMT SOB standoffs within the design, and to space off and be able to remove without any loose hardware, they wanted to be able to remove this top panel. They applied some of the surface mounted panel fasteners on top here, and you can see the solder fillet that has formed at the perimeter that holds it in place. With the plastic cap, we were able to accommodate the customer's specific color wishes, and in this case they like this color blue. The reason why they chose this fastener was previously they were considering a snapping in panel fastener. Now, snapping in doesn't put as much pressure on the board as broaching in does, but it was still more than they wanted to risk. Their fear was these were expensive boards. They did not even want any sort of pressure from the competitor's panel fastener potentially adversely affecting the board. So by switching to surface mounting the retainer on, no issue there, no pressure applied to the board, and then later pressing down and popping the plastic screw onto the retainer made them much more confident in their design. Anytime an assembly is subject to vibration, there's the concern that any loose screw could back out from the thread it was mated with. One way to get around that is to use a locking self-clenching fastener, and there's several different styles available from PennEngineering, but they all have one or another style of locking feature. Typically, this is a deformed thread or a modified thread or a thread with a nylon locking element. All of these act in a way that grabs hold of the mating screw and prevents the ability for it to back out under what's known as vibrational loosening. The reduction or elimination of PFAS substances, otherwise known as forever chemicals, is a growing trend. Customers may choose to use a patch screw in order to prevent vibrational loosening. However, they may be uncertain of the actual PFAS-free nature of those screws. Instead, they can choose any of our standard lock nuts. They are all PFAS-free, and therefore they can just purchase and design in a standard screw and get the same vibrational loosening benefits with our clinch nuts. This application is good to show how choose what you need based upon that specific part of the assembly. In this case, this leg has a repeatable 15 cycle repeatable lock nut in it. But this part of the assembly just has the SL lock nut, which is typically 1 to 3 cycles of repeatability. Here's why. This is part of the leg leveler. So when they need to calibrate the product, they need to be able to thread in a screw and back it out and slightly turn it in or out to calibrate it to make sure the playing surface is appropriately level. This is simply part of the basic assembly of the chassis, and its purpose is simply to hold two pieces of metal together. But with all the rattling and shaking and tilting of this machine, you don't want it to vibrationally loose. So here, they just don't want to put Loctite on it. They put this in, the SL lock nut grabs the thread and it's not going to let it back out. Here, they do want the ability to remove, reassemble, and fine-tune the calibration of the leg leveler. The RT free running lock was chosen in this application because this sort of situation is going to require many more than 15 cycles of repeatability. This will be used typically in apartment complexes, college dormitories, places like that. So when the repair person comes in, does work on it, they simply remove the clamp load from the joint, and now the screw runs free. When they want to reassemble it, it's a free running screw into the thread, and then applying a clamp load, it locks it in place, and it will resist all that vibrating and shaking that's going to occur as the laundry equipment does its job. But again, the key thing is this can be done repeatable many, many times with no fear of losing the locking feature. Over the last 10 years, we've seen more and more applications where either the product itself was tried to be made smaller, more components are tried to be fit within that product, or more likely try to do both at the same time. We see thinner and thinner sheets, people requiring closer to edge applications, and therefore the micro PEM line of fasteners has been constantly added to over the past 10 years. This is an application that started from one of those PEM edge teardowns. We noticed that this customer had over 100 screws, basically at the intersection of the different keys in the keyboard. And a screw is theoretically removable, but we found that these little M1.2 screws, that patch works very well. And about a third of the time, the screw broke, the screw stripped, it camped out. So the reality was they were using screws that were removable, but they couldn't remove all of them, and therefore they certainly couldn't remove them all and replace them all. So we presented them this idea of the tack pin, and they agreed that they had a failure rate of about a third as well in removal. So effectively, it was a permanent assembly. So we suggested the tack pin, and they, to this day, are still using it and have happily replaced over 11 billion at this point in time M1.2 screws. But again, it's not just the cost of the screw that they're saving. It's all those other costs, what we use the term total installed cost. For example, think about 11 billion screws. They had 11 billion tapped holes. So they had to purchase enough taps to tap 11 billion holes. I don't know how long a tap lasts, but that's a cost that someone had to purchase that they no longer needed to purchase. That's the sort of thing. They never had a failure due to cross-threading because they couldn't cross-thread a tack pin. But they had to have failures from cross-threading when they used screws previously. It's all those additional risks that are gone when they chose to switch to a tack pin. This application with very high cosmetic requirements, the customer was going to use screws until they realized they had absolutely no ability to fit the screw into the small confined space. So they came to us and asked, can we design a tack pin to do so? And we had never designed one this small before. It was a third smaller than anything we had ever designed. But we figured out a way to do it. And now in these buttons, there are 2 tack pins per button, 3 buttons per case, and you can see here, the back side of these 2 buttons, the heads of the 4 tack pins. And also, we have the knowledge with our Hager side of the company about the importance of proper installation as well. So this material is anodized aluminum. It comes in many different colors, but with anodization, you need to worry about proper installation, because if not, you could put that little crack in the anodized surface, sort of creating what's known as spider webbing. And so it wasn't just enough for us to come up with a fastener that would fit in this very, very tight space. It was to design one that we would know would be able to be installed with correct pressure to prevent that risk of cosmetic damage. So it had to be physically the right size to fit, but it also had to not cause them any cosmetic issues. And we're able to solve that with this application, and they've been using this for several years now. This is one of the earliest design wins we had for the tax cert. In this application, this is a product that you swipe credit cards through, and this is the sort of product that never gets repaired. It gets replaced if there's a problem with it. So previously they were using screws that had a thicker head, but they would never take this apart, so they were never going to back out those screws. So that was the perfect opportunity to consider an alternative assembly method, and they chose the tax cert. In this application, a magnesium laptop frame, the thread forming screws were replaced with taxers. One of the reasons the customer wanted to replace them was they knew with the thread forming screws they were only getting a thread strength as strong as that brittle magnesium was. Also, they knew that they could not expect to be able to remove all of the screws, that some would cross thread on the way in, some of the drivers were stripped. Ultimately, even though they were removable screws, the reality was they weren't all removable, and if one couldn't be, then the entire assembly couldn't be. So in this case, they chose the TK4 taxers and were able to replace every one of those screws, and therefore saved a lot of money in the assembly process. This application, the customer wasn't even aware of self-clenching fasteners before we introduced it to them. They had always used weld fasteners, and to them it just seemed natural. That's what they had always done. What else would they do? But we presented them with options. We had done a teardown a couple of their products, and they asked us to come present to them. And what we learned was, yes, they had a concern about welding. Their concern was the ability to get, with the weld equipment, up into tight corners. That's much less of an issue with tooling necessary for clinching fasteners. So they were able to put fasteners into positions that was more difficult for them before. The positional tolerancing of the thread, a truer position occurs with a self-clinching fastener than it does with a weld fastener. And what was very important to them was now that they had alternatives. Prior, this panel had always been stainless because they would weld stainless fasteners to it. So it's simpler to weld similar metal, so they had to use a stainless fastener into a stainless panel. Well, they learned they could switch to clinching, so they liked that because of the positioning. It enabled the clinch tooling to get up closer to a corner. But with the next phone they designed, they changed this stainless to an aluminum panel because now they could clinch into aluminum. They weren't beholden to having to weld similar metals together. They can work with dissimilar metals now that they chose to clinch, and it greatly opened up alternatives for them in their design. The PEM Ghost magnetic release fastener enables invisible, secure, and tamper-evident assembly. A magnetic tool that mimics the location of the fasteners is required for proper disassembly. By doing so, this prevents unauthorized access because you must have the proper tool in order to disengage the fasteners. PennEngineering has a wide range of panel fasteners, also known as captive panel screws. Two panels can be held together with a loose nut and a loose screw. People often choose self-clinching hardware to eliminate half the loose hardware. You clinch in a nut, you eliminate the loose nut where you clinch in the stud, and you eliminate the loose screw. But you still have 50% of the assembly is a loose component. When a customer adds a panel fastener to the mix, they've eliminated all the loose hardware. A panel fastener on one side of the assembly, and on the other side will be a clinch nut or standoff for some other internally threaded fastener. And then you have no loose hardware whatsoever to handle. These locations also are often touch points, something where the end user ultimately is going to access this frequently. And a customer will want the conveniences brought by certain features within the panel fastener. So within our line of panel fasteners, there's obviously, as you see graphically here, many different styles, many different sizes and shapes. All will do one specific benefit or another, or several within that one panel fastener, and we'll discuss that on these later slides. This application was one of our first big wins for a matte thread panel fastener, and we specifically won this business against our competition. We're both vying for this. We both made presentations of our product to the end customer. This end customer's product at the time is the most expensive server in the world. It was bigger than anything was ever built at the time. And the key thing is, for someone to spend that much money on a server, they want all the benefits they could possibly provide to the customer who's buying that from them. So they want every convenience, every benefit they can. And one of those is the knowledge that their end user will never be able to cross-thread this panel fastener. They could assemble, disassemble, reassemble constantly with no fear of cross-threading. So when we were bidding against this, against our biggest competitor, we had this feature and they didn't. And when we handed this sample panel that you saw on the previous slide to the customer tried it themselves, felt that, as I described, they felt that in their fingertips, and they said, well, we want this on our part. And we said, great, well, give it to you. They said, well, how much? And we said, it's free. And then they said, well, then we really want that. And that's the point. You are providing to the customer and then ultimately their customer a benefit that we always talk about total installed cost. Well, that's a true part of it. It's the convenience for the end customer and then the knowledge that they cannot cause themselves any sort of financial damage via scrap or lost time. So it's very good for the assembly of the product, and it's also very good for the end use of the product. In this application, there's really two stories. One is about the pin. The pin is a more aggressive taper on the pin. And this is because some customers want that convenience of aligning up this base plate as these are moved into and out of the rack. Now, if they're concerned about the sharper pin to help them because they think there's an alignment issue, well then why not add the matte thread feature to the panel fastener? Misalignment accommodating thread is what will benefit the end user. So again, they're already concerned, they feel, about alignment issues, so they want a sharper pin. Well, let's go with a belt and suspenders solution here and add the matte thread feature to the panel fastener as well, and they can rest assured that this will be able to be disassembled and reassembled with ease. A large benefit available with the CAPS design, the colored access panel screws, is the fact that we can mimic any particular color that a customer wants. And in this case, also a special design of the knurl was able to be accomplished. So both the color and the shape of the knurl was created specifically for this customer. Seen here is a close-up of this section of the mass spectrometer when they open it up to do work inside, repair work inside. So the PF30 is chosen that when this is hinge closed, it threads in and locks it in place. They use the PTL2 here for two reasons. About this pin, it's acting as a rotation point. So this product, as it's raised and lowered, it's rotating around this pin. So that's what's going on here. But they can also retract it and then completely take this cover off and then replace it, turn slightly, and now the plunger closes, it goes through the hole, it's locked in place, then they can close the lid and thread it in with the PF30. In this application, the customer required a small footprint. The PFHV satisfied that, but they also had a very close centerline to edge situation. In this bracket here, they had a centerline to edge concern on three sides. So by switching to a flaring style retainer, just like with any other fastener, if the fastener deforms, we do not care what the panel hardness is, nor what the centerline to edge concern is. So we made a special product here, put the flaring shank on the panel fastener, and that was the solution for them. In this application, they were concerned about loose hardware, loose screws being disassembled and then dropped inside the enclosure. This is very high voltage that could be very dangerous and cause problems. They didn't want to add the cost of a full panel fastener, but they still wanted a captivated screw if possible, so the SCB was chosen. These roller bearings are available in both clinching and flaring versions. They can enable the elimination of expensive drawer slides and help in reduced footprint applications. This server customer made the decision to switch from drawer slides to the roller bearings, and they've continued to use that for over a year and a half on this project. There are three styles of wrangle fasteners. The RAS will clinch into metals and will accept a machine screw. The RAA is made from extruded aluminum. It will clinch into softer metals and accept a thread forming screw. And there's the SMT-RA, which is applied to PC boards by the reflow surface mounting process. These parts help create right angles in assemblies. You can do that otherwise with bent flanges or tab cutouts or angle brackets, but those require additional work, especially things such as angle brackets. As you see here, this would require the physical manipulation of 5 components: the angle bracket itself, 2 loose nuts, and 2 loose screws. Even if you clinched in 2 of the nuts into the bracket, you still would have the bracket and 2 loose screws. So at a minimum, 3 components, typically 5 in this situation. So there's just a lot of extra labor required for assembling this and to create that right angle. Tab cutouts, you can create that cutout during the stamping process, and that's fine, but now you've created a hole in the product. This can be an EMI or an RFI concern, certainly a opportunity for dust or dirt to enter the inside of the assembly. So these parts clinch in. They clinch in these 2 areas of the wrangle itself. They're still deforming metal just like any other PEM fastener, but again, they can make either a total installed cost savings or a more cosmetic assembly than you would get from these other methods. This is an application where an angle bracket was replaced with the wrangle. In fact, this engineer had described to me how he needed, quote, 3 hands to assemble this because you had the bracket, the 2 loose nuts, the 2 loose screws, a lot of inconvenience and time necessary to actually manipulate and assemble. So by switching to a wrangle, he now has the wrangle clinched into this faceplate. There's now only 1 loose screw, the screw that comes up from the bottom. What's also important to them was the fact that they had the nice flush surface on this side of the faceplate. So now, as opposed to the head of a screw showing, they now have a clean surface that they're able to put a label over the top of, and there was nothing showing. There was no screw head. It was a nice, good cosmetic solution for them. As you'll see on many of these applications, the fastener is used to replace brackets. So the wrangle here in these locations was used instead of what had been loose bracketry and loose hardware. This application does a very good job of explaining total installed cost. What we have here is just one surface mount wrangle in place here. And relatively speaking, that surface mount wrangle placed in a tape and reel as a fastener itself can be deemed more expensive. They all told the cost of the fastener and the installation for this customer was about 50 cents a piece. But what they replaced was a lot more. It was $3 because it was a special bracket, multiple pieces of loose hardware, and then a lot of labor necessary to make that assembly. Now, very fast off the pick and place machine. And so again, the fastener that's a bit more expensive saves a lot of money in total installed cost. Both the SF and the SFP versions, we are clinching very hard into the bottom panel. But in the top panel, be it metal or in the SFP, top panel can be stainless, we're moving material into an undercut, but it's not as aggressive of a clinch as you find in the bottom one. So this enables these designs to also be used as a hinge. Most people are just using them to hold 2 panels together, but they can also be used as a hinge, and I'll show some applications of those. Now, the SFW version does include a washer, and this wave washer is assembled between the 2 panels. Now, in these applications, which we'll show, the hinging action is controlled. You'd move it and would stay in position, move it and stay in position. With this style, it would hinge and become less and less friction over time. And for some designs, that wouldn't be appropriate. For some, it would be. So depending upon the application, I would recommend trying this style first if hinging is the desire. Ultimately, then the SFK, this design is for combinations of a top sheet being metal and a bottom sheet being something non-ductile like PC boards, plastics, cast magnesiums, and aluminums. So the spot fast is used to hold two panels together. And as seen here, you can see these two dissimilar metals, brass and aluminum, held together, nice and flush surface on the top. It's either going to be flush or, depending upon the thickness, subflush on the bottom. The important thing here is this would have been very difficult to weld together, these dissimilar metals. And so that's where the spot fast can really come into play. Also, this image here shows something that kind of goes against what's in our catalog. In our catalog, we indicate a minimum sheet thickness for top and bottom, but one of our PennEng services, being our applications group and our tech lab testing, was able to prove for a customer that something like this is possible. This top panel is only 5 thousandths of an inch, 0.013 millimeters thick. But as long as you consider its thickness and the thickness of the bottom panel, add those two together. If you pick an L dimension of the spot fast that is equal to or less than that, then this will work as long as the top sheet is the thinner sheet. So you can see, barely can see here, the spot fast, it's holding this top panel down. This would have been a difficult situation to try to weld as well, even if there were similar materials, because this is so thin, you definitely get a concern about burn through welding. So again, another example here where the spot fast can be an alternative in your design thoughts. We'll discuss several applications now. This first one is a server mounting rail. Previously, the customers were using rivets, and the rivet head, the bulbing of the rivet, took up some real estate that they wish they didn't have to, and they would have preferred a streamlined design. And as you can see here, they replaced those rivets with spot fast, and now it's a nice smooth surface, and they were quite pleased with the result. What you see in this application, or more appropriately, what you don't see in this application, are the spot fasts that are being used to hold these brackets to this front door. For them, it was a nice clean assembly, but most importantly for them was these wires. They did not want the risk of a situation like this or this, that there was an exposed screw that the wires could snag on. So here's a nice smooth, nothing to catch the wires, and they could safely trust that their assembly would work well. This is an example of the spot fast being used as a pivot. Not the version with the washer, but just the standard spot fast. You can see it's installed here. They chose the SFP because there's stainless materials involved here. And this actuator pivots between 10 and 15 degrees, back and forth, back and forth, back and forth. And they've got a nice flush hinging action here by utilizing the spot fast. Here's an example of where, when a product is a touch point, something that the end customer is going to use, that can be a real concern for the OEM, and they want to give all the conveniences and make their product feel robust by making it feel stronger. So in this case, previously they were using a flared rivet, and the problem with the flared rivet is that, do you rivet it perfectly? Do you under flare it, over flare it? There's an inconsistency in the feel, and they did not like that. So they switched to our spot fast. In this case, it is using the version with the washer. The washer's in the middle here. As you can see, we're flush at the bottom, flush at the top. Theirs were proud of both surfaces. So that can be a problem. It was for them, for the extra space that was required. So in this case, they were able to replace it, and with the washer, they get a nice, consistent, repeatable hinging action. The spinning flare nut is a product that can help eliminate all loose hardware. What often can occur is you may have a clinched stud, one of our clinched HFH studs perhaps, in the top panel, and then a loose nut would be threaded onto it to hold the two panels together. But for certain applications, any loose hardware is something that is not wanted. So as shown here, once this part is pressed into this embossed mounting hole, it's going to spin freely and it won't come out. So there's no torque resistance at all. It will spin free. So when you back off this nut, these panels separate. When you reassemble it, they'll come together. Example, one customer who makes electrical boxes that go up on telephone poles, they had said, well, we would use one of your clinched in studs and then a wing nut to hold the door closed. But the problem was in inclement weather, someone would go up on a ladder, back off the wing nut, and potentially, especially if they're wearing gloves in the winter, let's say, they may drop that wing nut down into a snowbank, down onto the ground, and then it'll be difficult to find a replace. So by putting on a part such as this that's captivated into the panel, you have the clinched in stud, spinning flare nut, you have no loose hardware, nothing can get lost, it'll all stay in the assembly, and so it's easy to assemble, disassemble repeatedly. This is a common application. You have a power connector, cable terminal lug typically. You'd have the ring tongue, and you'd place this over a clinched in stud, maybe one of our HFHB bus bar studs. But previously, you would have to then add a washer and then add a loose nut. Loose components that must be handled, hopefully not dropped, and when they're removed, you hope you don't drop them. So by flaring this nut into position on the ring tongue, you now have an assembly with no potential of loose hardware being dropped or placed into the wrong position. Standoffs are another style of very popular self-clenching fastener, just like the nuts and the studs are. And like them, they come as well in different materials and different hardnesses designed for different panel materials, as well as panel thicknesses and different configurations depending upon what the application requires. By choosing to space this PC board off of this metal panel with self-clenching standoffs, the customer eliminated the extra labor required by using snap-in fasteners as well as loose hex spacers. This customer switched from a welded stud because they're having issues with the true position of the internal thread. With self-clenching, you have a truer position than you get with welding. And in this case, they chose the style of blind standoffs so that when they were installed, they were able to grind and then paint over them, and you cannot see anything on the surface. So it provided truer position, which they required, and was also a very good cosmetic solution for them. The benefits of keyhole standoffs is that they greatly reduce the amount of loose hardware required to assemble a product. Instead of having several standoffs and therefore several loose screws, you could have one internally threaded standoff and just one loose screw, and the rest of the standoffs be keyholes, where you would drop the panel down, the panels would have keyholes cut into them. Drop it over the top of the keyhole standoff, slide it into place, and then with just the one loose screw, tie the assembly together by threading that into the one internally threaded clenching standoff. As seen in the sample panel, you can see the keyhole shape in the top panel gets dropped over the keyhole standoff and then slides into place. And here, with a flush nut in the bottom panel and then a panel fastener in the top panel, you have absolutely no hardware to deal with. So this can be assembled, disassembled repeatedly with no need for any loose hardware to be concerned about. This was a cosmetic solution here where the customer did not like the look after the weld. There was a marring of the finish, and people would see this constantly, so they just did not like that, so they switched to clinching instead. I think it should also be noted that with this short keyhole used in a 90-degree turn from the typical use, you can see how they are utilizing gravity to help keep the tray rails in place. So they're using gravity here to let it simply hang on the neck of the keyhole standoff, and it's sort of a unique use of this product. Instead of this PC board panel held in place with a bunch of loose screws threaded into standoffs, the customer now has just two screws used to tie the panel down, and the rest of the locations are these keyhole cuts where the panel's dropped over the keyhole, slid into place, and then the two screws are assembled to complete the process. Perhaps the most important thing to ensure that a clinching fastener will work is that the fastener is harder than the panel. And working with stainless steels, that is a concern. So in this bulletin, we gathered all the fasteners throughout our catalog that will work in stainless steel to put them all into one catalog. And so when customers are working with stainless panels, if they turn to this bulletin, they'll be able to see the full range of fasteners available to them. These two images here are examples of what happens when the fastener and the panel are too similar in hardness and there's not enough of a separation. Here you can see what had been in the previous picture, a nice sharp point, that's been completely smashed downwards. We've gotten some material in the undercut, but as you can see here, it's not as filled in as it could or should be. What's worse in this image is you can see that actually this has bulged outwards. The press head coming down, pressing on this part, this panel being too hard, we're now squeezing the fastener. So you're either going to have tight threads or threads that aren't going to work whatsoever. But as you can see here, the problem with this lies in the fact that we did get some material to move. Again, we kind of smashed these two things together, the fastener and the panel. So this will hold, but not nearly as well as it would or could. And therefore it's prone to failure somewhere down the line. This is an example where it's not even close to happening. The fastener really gave up quickly here, and you can see the shank collapsed inwards, and this part, though it might hold in for a little bit, it'll fall pretty quick. But the problem here is this fastener will hold in for some time. It's prone to failure, and again, that's just a matter of, as you can see here, the fastener did not keep its shape. It lost it, and therefore this is an example of the panel being too hard, the fastener. This is the sort of thing, cross-sectional images, we can do mounts of installed parts and help troubleshoot what the exact problem is. And again, often we find that the panel is harder than it should be. The two fasteners on the right show the sharp details that define the clinch area. However, the fasteners on the left shows what happens when they are attempted to be installed into a panel that is too hard. Those features are destroyed, and therefore the fastener cannot hold in as well as it should. This is an example of the most common error where a customer is using a 300 series stainless nut trying to clinch it into a 300 series stainless panel. It just won't work. You're mashing them together. You don't have the proper hardness differential. It also shows an example of you do get what you pay for. And that here is an example of not the proper support for the application. The customer sought help. The person they bought the fasteners from did not know the answer. They ultimately found a PEM distributor, and the PEM distributor was able to educate them on the proper fastener to choose for their application. This is another example where cosmetics came into play here. Again, weld studs were what they were using previously, but there's a cosmetic issue with that. They have the weld spatter concerns, appearance as well of the welded joint. So by switching to a clinch stud, a nice clean finish they were able to achieve. As we've discussed, we have many parts that look identical in size and shape, but it's the material that they're made out of which makes the difference as to what materials they can go into. So for this customer, it's actually easy for them to switch. They previously made their chassis out of aluminum, and they'd chosen our 300 series stainless fasteners to clinch in there. Once they wanted to change to a stainless panel, they knew they could use the same size and shape part, but instead they would choose the parts that are made of a 400 series stainless because they'd be heat treated and therefore hard enough to go in the panel. So not much change to the bill of materials other than simply the part number. They certainly don't need to change any of the mounting hole sizes or any of the other details in their chassis. They just simply had to choose the proper fastener now for their switch from aluminum to stainless panels. Snap-top standoffs were created to allow toolless assembly of one panel to be spaced from another. There's no requirement of any screws to create the assembly. You simply press down the mating panel on top of it. It'll snap into place, and you'll also be able to remove it by unsnapping it off the standoff. In this application, the PC board is able to be snapped right on top of this snap-top standoff, and by eliminating what had been a self-tapping screw, there's no risk of any potential damage to anything else within the assembly. It's simply a toolless assembly and disassembly. This customer liked the idea of the toolless assembly, but instead of choosing a broaching style of snap-top standoff, they chose the new surface-mounted version. The tie D cable tie mounts were created to eliminate those lesser alternatives shown on the previous slide. They have a nice rectangular through hole through which the cable tie can be run through, and then the wires can be bundled up and the zip tie tied off, and now you have a nice secure attachment for the wires to the assembly. A couple of the lesser alternatives to the cable tie mounts are shown here. The most common is probably these adhesive mounts. The problem with them is they're adhesives, and they will fail over time. You just don't know when that will be. They also are much lower strength than the rating for the cable ties that they work with. So you may think you've got a strong assembly because the cable tie is rated for 40, 60, 175 pounds. But the reality is it's only as strong as its weak link, and that would be the adhesive mount. Those adhesive mounts are rated for much lower strength than this cable tie. So they will either fail over time due to the adhesive drying out, or simply because you pulled on them much harder than that adhesive could withstand. Another style are these lances in the chassis. Now you can make a lance for free when you stamp out the metal, and that's fine, but ultimately when you use those as a fastening point for a cable tie, oftentimes the cable is going to be up against a sharp edge, and if there's any sort of vibration occurring during the use of the product, you're going to slowly start to abrade that cable, and that could cause a catastrophic problem ultimately. So these exist, but they are lesser alternatives to tidy mounts. This example here shows two main benefits of the TD fastener. The first one we discussed already, and that's the fact that they're not adhesive mounts, and those adhesive mounts will fail. A product such as this is sitting out in the sun on the side of the road, and so that adhesive mount will ultimately fail. That peel and stick adhesive will fail. You just don't know it's going to be next Wednesday, and you can plan the repair accordingly. So that's certainly a concern, is when will they fail, when will have to be replaced. But another one is a comment made to me by a couple engineers where separately they said the same thing, is they like these because they know they want their wiring to be routed in a certain manner. And if they put the TD mounts in place on the print, then there's only one choice. The wires must be attached to them and follow their lead. But with adhesive mounts, the fabricator could peel and stick and put them here and here and here and here in any number of locations. So engineers like the fact that if they know for a fact, got to have the wires running in a certain manner, by utilizing the TD mount, there's no choice but to follow that. Once this customer learned of these TD mounts, it was an easy switch for them to go from the adhesive mounts that they were not happy with, that had been failing, to switch to the TDs. And that's because they were already using a lot of other clinch fasteners elsewhere within their design. So they had faith in the clinch fasteners. So instead, they decided to replace those adhesive mounts in these locations with the TD. The Veramount fastener can work with basically any panel material, and there's multiple methods of applying them to that panel. But I think for the most part, you would see these applications appropriate for materials such as composites, carbon fiber, fiberglass. These are materials that are not ductile metals, so we wouldn't want to clinch into them, and typically non-ductile metals, we would then say, well, try to broach into them. But with composite materials, they lose their integrity when you cut into the fibers. So that's not desired either. So what would be is a product such as this. You have a standard PEM stud or a nut or standoff clinch into this base plate, and then the most common would be the base plate would be adhered to the composite material by adhesive. It could be peel and stick, very high bond tape. It could be glue adhesive. It also could be laid up during the panel creation process. But again, I think what you will most likely see are opportunities for materials such as composites that you would then have this part bonded to. Shown here is a perfect situation for the Veramount solution. In this case, the customer is working with two of these foam panels. They kind of have that silver skin that graphics will be printed on. They have no integrity, no strength to them whatsoever. You're not going to clinch something into it. You're not going to broach something into it. Yet the customer still wanted to have a nice, strong metal to metal screw thread assembly. So here they chose adhesive. They take adhesive, put it on the board, the Varamount is placed on top. You see the glue comes up through the holes and creates a sort of mushroom cap which holds it onto this panel. And now they can come through with a loose screw into the metal internal thread of the Varamount, and now they have a nice strong metal-to-metal assembly in something that they would never be able to do with any sort of clinching or broaching hardware. The stick screw system is a series of up to 130 screws that are on one continuous stick, and as you advance the parts, they break off and advance to the next screw. What you can do here is you develop a seating torque, and that's based upon the physical properties of the material. What material is this? Is it aluminum, stainless steel, brass, heat-treated steel? What's the cross-sectional area right here? So again, you can define the seating torque that you want for an application by choosing the appropriate diameter and material properties. So again, as it's threaded into the screw, then it comes to that seating torque, it breaks off here, the tool advances to the next screw, and you can continue just to go in order. Stick screws can also be used in applications where it's not convenient or possible to clinch a product in. Shown here is a common use. These data plates can be attached to materials such as cast aluminum or cast brass material and held in place by just screwing the stick screw through the data plate into that material. SI inserts provide strong metal internal threads into plastics in three basic ways: ultrasonic or heat staking, molded in, or pressed in. They're also available in multiple materials. Brass is very common, but Standard Insert is one of the rare brands that offers these products in stainless steel and, more importantly, also in aluminum. With aluminum, you'll find that is often chosen to help lightweight a design. And here's an example where the customer switched from a brass insert to the aluminum version in order to reduce its weight. This is a typical application where a nice strong metal thread is required, where screws will be repeatedly inserted and removed from that in an assembly. Here's a common use where a battery is held in place, so that's something that needs to be repaired and replaced often. So that being the case, you use a screw into a nice metal thread. But think of the applications that don't require removability. If that is your design, then you can eliminate the loose screw, eliminate the brass insert, and replace it with a tack cert instead. So removability, absolutely, insert and loose screw is the way to go. But if your design is not going to be disassembled, this is the situation to consider a tack cert as its replacement. The different SI styles available help this customer switch his method of production. Originally, they used the NFPC style and pressed these parts in post-mold. Then they decided they wanted to insert mold them, and they were able to switch to the IBC style. The Atlas brand of blind threaded fasteners are appropriate for application. One option available to Atlas fasteners is to put a ring under the head, and that does help in applications that require some level of sealant. An externally threaded part is also available with an Atlas style feature, and in this case the customers were concerned about cross-threading, so the mat thread misalignment accommodating thread feature was added to this product. We encourage you to use our free PennEd services. We'd be honored if you felt that we were part of your engineering department. With our global footprint, we are there to serve you throughout the world. We can work with you from just the beginning of the concept straight through to when it comes off the production line.